प्यारे बच्चों, ਅੱਜ ਦੇ ਪਾਠ ਵਿੱਚ ਆਪ ਸਭ ਦਾ ਸਵਾਗਤ ਹੈ। ਅੱਜ ਦਾ ਸਾਡਾ ਡਿਸਕਸ਼ਨ ਇਲੈਕਟ੍ਰੋਡ ਪੋਟੈਂਸ਼ੀਅਲ ਐਂਡ EMF of a galvanic cell ਬਾਰੇ ਹੈ। ਇਲੈਕਟ੍ਰੀਕਲ એનર્ਜੀ ਬਹੁਤ ਸਾਰੇ ਕੈਮੀਕਲ ਰਿਐਕਸ਼ਨਸ ਵਿੱਚ ਬਹੁਤ ਇੰਪੋਰਟੈਂਟ ਰੋਲ ਅਦਾ ਕਰਦੀ ਹੈ। Electrochemistry is that branch of science which deals with the production of electricity from energy released during spontaneous chemical reactions and use of this electrical energy to bring about non-spontaneous chemical transformations. Sodium hydroxide, for example, which is used in the manufacturing of paper, textiles, soaps and the detergents, is produced by passing an electric current through an aqueous solution of sodium chloride. Chlorine, essential for the manufacturing of plastics such as polyvinyl chloride or PVC, is obtained in the same process. Aluminium metal is also produced in an electrochemical process, as is pure copper for use in electrical wiring. The basis of these processes are redox reactions, which we have already learnt in our previous classes. Most chemical and biological reactions are redox reactions. Can you list few examples? Well, they are used in burning fuels, obtaining energy for domestic, transport or industrial purposes, digestion of food in animals, photosynthesis to capture energy from sun, extraction of metals from ores and many others. Hope you must have realized by now that study of electrochemistry is important for creating new technologies which are eco-friendly. In fact, redox reactions keep us alive. This raises many other questions in our mind, like what is an electrochemical cell? Why does electric current flow? What are electrodes? How many types of electrodes are there? Why do these electrodes develop positive and negative charges on them? What is electrode potential? Which redox reactions take place at the electrodes? What is EMF of a cell? हाँ, आज ਅਸੀਂ ਇਹਨਾਂ ਸਭ ਬਾਰੇ ਗੱਲ ਕਰਾਂਗੇ। Before we continue, we will understand what potential difference is. There are two types of electrodes, positively and negatively charged. The flow of electric current in an electrochemical cell indicates that a potential difference exists between the two electrodes. To understand the potential difference, let us study the redox reactions taking place at the two electrodes.
Let us have a look at an electrochemical cell. When an electrode, say copper, is immersed in a solution of its ions, then either of the following three possibilities can take place. The metal ions, that is, the cuprous ions, Cu2 positive, may collide with the electrode and do not undergo any change. Cuprous ions, that is, Cu2 positive ions, may collide with the electrode and may gain electrons and get converted into metal, that is metallic copper. Have a look at the equation shown on the screen. Cu2 positive plus 2 electrons give copper. This is the reduction reaction. Copper atoms on the electrode may lose electrons to the electrode and become cuprous ions and go into the solution, that is, oxidation occurs. Copper gives Cu2 positive plus 2 electrons. This is oxidation reaction. If a metal has a relatively high tendency to get oxidized, its atoms will lose electrons readily and form cuprous ions, which go into the solution. The electrons lost on the electrode acquires a slight negative charge with respect to the solution. Some of the cuprous ions from the solution will take up electrons and become copper atoms. After some time, an equilibrium is established as shown on the screen. Copper in solid state on the electrode is in equilibrium with copper ions in the solution, that is Cu2 positive, plus 2 electrons on the electrode. When such equilibrium is attained, it results in separation of charges, that is, negative on the electrode with respect to the solution. Similarly, we see that if the metal ions have relatively greater tendency to get reduced, they will take electrons from the electrode. As a result, a net positive charge will be developed on the electrode with respect to the solution. This will also result into separation of charges, that is, positive on the electrode with respect to the solution. Due to separation of charges between the electrode and the solution, an electrical potential is set up between metal electrode and its solution. The electrical potential difference set up between the metal and its solution is known as electrode potential. Thus, electrode potential is a measure of tendency of an electrode in a half cell to gain or lose electrons. The electrode potential may be of two types. Oxidation potential, the tendency of an electrode to lose electrons or to get oxidized, is called its oxidation potential. Thus, oxidation potentials give the tendency of an electrode to lose electrons as shown on this screen. Metal in solid state is in equilibrium with metal ions in the aqueous solution, that is Mn positive plus n number of electrons. Example, zinc in solid state is in equilibrium with zinc ions in the solution plus 2 electrons. Hydrogen in gaseous state is in equilibrium with 2 hydrogen ions in the solution plus 2 electrons. Reduction potential. The tendency of an electrode to gain electrons to get reduced is called its reduction potential. Therefore, it measures the tendency of an electrode to gain electrons as you see in the examples on the screen. Metal ions in the solution, that is Mn positive plus n number of electrons, are in equilibrium with metal in the solid state. 2 hydrogen ions in the solution plus 2 electrons are in equilibrium with hydrogen in gaseous state. It is evident that the oxidation potential is the reverse of reduction potential. For example, if reduction potential of zinc is minus 0.76 volts, its oxidation potential is plus 0.76 volts. Let me remind you that according to the present convention, the half-cell reactions are always written as reduction half reactions and their potentials are represented as reduction potentials. These are called electrode potentials. The electrode potential depends upon the nature of the metal and its ions, concentration of the ions in the solution, and temperature.
आओ हुण EMF और cell potential of a cell ते विचार करते हाँ. Electrochemical cell consists of two half cells. The electrodes in these half cells have different reduction potentials. Therefore, they have different tendency to lose or gain electrons. The electrode having higher reduction potential will have higher tendency to gain electrons, whereas the electrode having lower reduction potential will have lesser tendency to gain electrons, rather it loses electrons. As a result of this potential difference, there is a flow of electrons from the electrode with a lower reduction potential to the electrode with higher reduction potential. The difference between the electrode potentials of two electrodes constituting an electrochemical cell is known as electromotive force or cell potential of a cell. This acts as a driving force for the cell reaction. The potential difference is expressed in volts. Therefore, the cell potential or EMF arises from the difference in the tendencies of the two ions to get reduced. It is equal to the reduction potential for the substance that actually undergoes reduction minus the reduction potential of the substance that undergoes oxidation. As we have already discussed, reduction occurs at cathode and oxidation occurs at anode. Therefore, EMF is equal to reduction potential of cathode minus reduction potential of anode. In the representation of an electrochemical cell as a convention, cathode is written on right hand side and anode on the left hand side. Therefore, EMF of a cell may also be written as shown on the screen. Thus, EMF of a cell may be defined as the potential difference between two electrodes of the cell when either no or negligible current is allowed to flow in the circuit. The EMF of the cell is measured with the help of a potentiometer. It depends upon the nature of the electrodes, temperature and the concentration of the solutions in the two half cells. For example, the EMF of a Daniell cell in which the concentration of aqueous solutions of copper sulfate and zinc sulfate in the two half cells is 1 molar at 298 Kelvin is 1.10 volts.
Children, let us now learn about difference between EMF and potential difference. The differences between EMF and potential difference can be grouped as shown on the screen. Let us now learn about the differences between EMF and potential difference. While EMF is the potential difference between the two electrodes when no current is flowing in the circuit, potential difference is the difference of electrode potentials of the two electrodes when the cell is sending current through the circuit. EMF is maximum voltage available from the cell, while potential difference is less than the maximum voltage obtainable from the cell. That is EMF of the cell. The work calculated from the EMF is the maximum work obtainable from the cell. But the work calculated from the potential difference is less than the maximum work obtainable from cell. Lastly, EMF is responsible for flow of steady current in the cell, while potential difference is not responsible for flow of steady current in the cell.
Let us now take another example of magnesium, which is more negative than copper and is a stronger reducing agent.
Children, you are looking at magnesium metal at atomic level. Magnesium atoms lose electrons to form magnesium ions. Metal ions gain electrons and get converted to metal. A dynamic equilibrium is established when number of atoms gaining electrons becomes equal to number of atoms losing electrons. The rod is now negative compared to the solution. The potential difference is now measured by introducing another electrode in the solution. Potential difference of the first electrode is measured with respect to the second electrode. This means that there is a need of a standard reference electrode.
Standard reference electrode. Since a half cell in an electrochemical cell can work only in combination with the other half cell and does not work independently, it is not possible to determine the absolute electrode potential of an electrode. We therefore find only relative electrode potential, standard hydrogen electrode. Let us now discuss about the standard hydrogen electrode. It consists of a platinum wire sealed in a glass tube and has a platinum foil attached to it. The foil is plated with finely divided platinum and acts as platinum electrode. It is dipped into an acid solution containing hydrogen ions in 1 molar concentration. Pure hydrogen gas at 1 bar pressure is constantly bubbled into the solution at constant temperature of 298 Kelvin. The surface of the foil acts as a site for the reaction. The reactions shown on the screen occur in this half cell depending on whether it acts as anode or as cathode. Let us have a look at the reaction which takes place when standard hydrogen electrode acts as anode. If standard hydrogen electrode acts as anode, then have a look at the equation shown on the screen. If standard hydrogen electrode acts as cathode, then the equation can be represented as shown on the screen. Standard hydrogen electrode is also regarded as reversible electrode, then the equation can be represented as shown on the screen. The electrode potential of an electrode can be determined by connecting this half cell with a standard hydrogen electrode. This electrode potential of a metal electrode as determined with respect to a standard or normal hydrogen electrode is called as standard electrode potential, represented as E0. Standard electrode potential are always associated with the reduction reactions occurring at the electrodes.
Children, let us now learn about measurement of standard electrode potential. To measure the standard electrode potential of a metal electrode, 1.0 molar solution of the electrolyte is taken in a beaker and a metal electrode is dipped in it. This constitutes the metal-metal ion electrode. Metal by metal ions Mn positive in solution. This half cell is connected to standard hydrogen electrode through a salt bridge. The electrodes are connected to a voltmeter. From the measured EMF of the cell, the standard electrode potential of the cell is calculated. This method is illustrated as shown on the screen. Measurement of electrode potential of zinc electrode. An electrode consisting of zinc rod immersed in 1 molar solution of zinc sulfate is combined with standard hydrogen electrode as shown in the figure. To obtain the cell reaction, we have to know what is oxidized and what is reduced to know the cathode and anode in the cell. We can determine this by measuring the charges of the electrodes because we know that in a galvanic cell, cathode is the positive and anode is the negative electrode. When we connect the two electrodes with a voltmeter, the proper measurements EMF of the cell are obtained only if the positive terminal of the voltmeter is connected with the positive electrode and the negative terminal of the voltmeter is connected with the negative electrode. If the connections are not correct, no reading will be obtained in the voltmeter. Thus, if the voltmeter gives the proper reading, it indicates that the electrode connected to the positive terminal of the voltmeter is positive, that is, acts as cathode, and the electrode connected to the negative terminal of the voltmeter is negative, that is, acts as anode. The electrons flow from the anode to the cathode. The cell may be represented as shown on the screen. The cell potential has been measured to be 0.76 volts. Thus, by combining with standard hydrogen electrode, reduction potential value of zinc has been found to be minus 0.76 volts.
Measurement of electrode potential of copper electrode in copper solution. To measure electrode potential of copper-copper ions, a cell consisting of copper electrode immersed 1 molar copper sulfate solution and standard hydrogen electrode is set up as shown in figure copper electrode. In this case, the hydrogen has greater tendency to lose electrons in comparison to copper. Therefore, oxidation occurs at hydrogen electrode and reduction occurs at copper electrode. Consequently, the hydrogen electrode acts as anode and copper electrode acts as cathode. Thus, the cell may be represented as shown on the screen.
The standard hydrogen electrode is the anode and the copper electrode is the cathode. Contact between the solutions in the two half cells is through a porous plate.
The porous plate acts as a salt bridge,
which permits the migration of ions but prevents bulk flow of the solutions. The direction of electron flow and the voltmeter reading are shown. The standard electrode potential of copper is plus 0.34 volts. Similarly, the standard electrode potentials of other metals can be calculated. Thus, the electrode at which reduction occurs with respect to standard hydrogen electrode has positive reduction potential, while electrode at which oxidation occurs with respect to standard hydrogen electrode has negative reduction potential.
Let me tell you that it is not always convenient to use standard hydrogen electrode as reference electrode because of experimental difficulties in its preparation and use. Let us list few of them. It is difficult to maintain unit concentration of hydrogen ions. The hydrogen electrode gets poisoned even in the presence of traces of impurities. It is difficult to maintain 1 atmosphere pressure of hydrogen for a long time. Therefore, some other secondary electrodes are used. The most commonly used reference electrode is calomel electrode with different concentrations. Saturated calomel. The saturated calomel electrode, or SCE, is a reference electrode based on the reaction between elemental mercury and mercury 1 chloride. The aqueous phase in contact with the mercury and the mercury 1 chloride, that is Hg2Cl2 calomel, is a saturated solution of potassium chloride in water. The electrode is normally linked via a porous frit to the solution in which the other electrode is immersed. This porous frit is a salt bridge. Standard electrode potential is equal to 0.24515 volts at 25 degree centigrade. Same is true in case of one normal solution. Potential difference measurement. Let us now learn how to measure the potential difference. Due to separation of charges between the electrode and the solution, an electrical potential is set up between the metal electrode and its solution. The electrical potential difference set up between the metal electrode and its solution is known as electrode potential.
In this case, copper is positive with reference hydrogen electrode having value of plus 0.36 volts, and magnesium is negative having a value of minus 2.36 volts at 298 Kelvin. EMF of a cell may be defined as the potential difference between two electrodes of the cell when either no or negligible current is allowed to flow in the circuit. The EMF is measured with the help of a potentiometer. It depends upon the nature of electrodes, temperature, and concentration of solutions in the two half cells. For example, EMF of a Daniell cell in which the concentrations of aqueous solutions of copper sulfate and zinc sulfate in the two half cells is 1 molar at 298 Kelvin is 1.10 volts. Let us now have a look at a galvanic cell. Electrochemical cells that use an oxidation-reduction reaction to generate an electric current are known as galvanic or
voltaic cells.
Because the potential of these cells to do work by driving an electric current through a wire is measured in units of volts, we will refer to the cells that generate this potential from now on as
voltaic cells.
It consists of an anode dipped in zinc sulfate solution, cathode dipped in copper nitrate solution. The two cells are connected by a U-tube called a salt bridge because it contains a solution of a salt that literally serves as a bridge to complete the electric circuit. Let us now have a look at the anodic compartment at micro level. Zinc ions and sulfate ions are present in solution. The cathodic compartment contains copper ions and nitrate ions. The salt bridge contains potassium and nitrate ions with a porous plug at each end. When the key is pressed in the anodic compartment, zinc releases electrons. That is, zinc releases zinc 2 positive in the solution plus 2 electrons. That is anodic reaction or oxidation half reaction. The anode is now negatively charged. The number of positive ions increases in solution and the equilibrium is disturbed. This is where the function of salt bridge comes into picture. The positive charges now become equal to the negative charges and the equilibrium is re-established. Let us now have a look at the cathodic reaction. Copper ions and nitrate ions are present in the solution. That is, copper 2 positive in the solution plus 2 electrons is in equilibrium with copper metal. That is, reduction half reaction. Cathode is positively charged. Reduction takes place at cathode. The number of negative ions increases in solution and the equilibrium is again disturbed. To maintain electrical neutrality, ions move through the salt bridge. The salt bridge releases positive ions into the solution, which are equal in number to the negative charges, and the equilibrium is again re-established. In this way, the current flows and process continues. We record the reading with the help of an ammeter.
So, students, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਸੀਂ ਅੱਜ ਦੇ ਪਾਠ ਦਾ ਆਨੰਦ ਮਾਣਿਆ ਹੋਵੇਗਾ ਅਤੇ ਤੁਸੀਂ ਇਲੈਕਟ੍ਰੋਕੈਮੀਕਲ ਸੈੱਲ ਬਾਰੇ ਬਹੁਤ ਕੁਝ ਸਿੱਖਿਆ ਹੋਵੇਗਾ. The possibilities which take place when an electrode is dipped in the solution of its own ions. We also learned how to measure potential difference, use of standard hydrogen electrode. We also discussed analogy for standard hydrogen electrode, types of electrode potentials, oxidation and reduction, and dependence of electrode potential on nature of the metal and its ions, concentration of the metal and its ions, and temperature. We also learnt about cell potential of a cell. We also discussed working of a galvanic cell and the difference between EMF and potential difference. Here are few questions to check your understanding about today's topic. The first one is, which electrode is taken as the standard reference electrode? And the answer is, hydrogen electrode is taken as the standard reference electrode. The next question is, name a metal which has a negative electrode potential with respect to hydrogen. And the solution is, these metals are magnesium, zinc, iron, etc. The next question is, how many kinds of electrode potential are there? The answer is 2 oxidation potential and reduction potential. Both oxidation and reduction potential for a metal are equal and opposite to each other as shown on the screen. My next one is, an electrochemical cell consists of how many half cells? And the answer is, an electrochemical cell consists of 2 half cells, oxidation half cell and reduction half cell. The next question is, which electrode will have higher tendency to gain electrons? And the solution is, electrode with higher reduction potential will have higher tendency to gain electrons. The next one is, what is the EMF of a cell? And the answer is, difference between electrode potential of 2 electrodes is called EMF of a cell. The next question is, list the factors on which EMF of a cell depends. And solution is, EMF of a cell depends upon nature of electrodes, temperature, concentration in half cells. The next question is, what is the name of U-tube which connects the 2 half cells? And the solution is, The U-tube is named as salt bridge. This is used to connect two half cells. The next question is, what is the function of salt bridge? And the reply is, the function of salt bridge is to complete the electrical circuit and to maintain the electrical neutrality of the solutions of two cells. ਮੈਨੂੰ ਆਸ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਅੱਜ ਦਾ ਪਾਠ ਚੰਗੀ ਤਰ੍ਹਾਂ ਸਮਝ ਆ ਗਿਆ ਹੈ। ਧਿਆਨ ਦੇਣ ਲਈ ਤੁਹਾਡਾ ਬਹੁਤ ਬਹੁਤ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਨਵੇਂ ਵਿਸ਼ੇ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ।